Module 2, Lecture B, Data Contracts. By the end of this lecture, you will be able to prepare NumPy, pandas, and sparse inputs that satisfy Scikit-Learn shape requirements, identify dtype and target shape issues before fitting estimators, and use dataset containers, feature names, cloning, tags, and diagrams for inspection. Input formats. NumPy array shapes. In Scikit-Learn, data is usually stored as a two-dimensional NumPy array, with rows representing samples and columns representing features. This consistent structure lets estimators clearly identify how many observations and attributes they need to process. Even data with only one feature should still use a two-dimensional format to avoid ambiguity. Many model errors come from giving data in the wrong shape. The input should match the format used during training, with each example as a row and each feature as a column. For a new prediction, even one apartment must be provided as one row, containing all required features, such as floor area and bedrooms. Keeping this structure consistent helps the estimator correctly recognize the data. In Scikit-Learn, the shape of your NumPy array must match what the model expects before fitting. The feature matrix should keep rows as cases and columns as characteristics, without accidentally swapping them. Keeping this structure consistent helps prevent validation errors and protects the integrity of training and prediction. Python code, NumPy array shapes. This example explains the basic shape rules for arrays in Scikit-Learn. Each row represents one sample, and each column represents one feature. It highlights the difference between incorrect and correct array shapes, so learners can prepare data in the format Scikit-Learn expects. We import NumPy for working with arrays, Scikit-Learn's linear regression tool for building a regression model, and Scikit-Learn itself to check version information. Together, these imports provide the basic tools for data handling and model fitting. We create one array for apartment floor areas and another for the matching rent prices. The floor areas are the features, and the rents are the target values. Both arrays are currently one-dimensional, but Scikit-Learn requires the feature data to be two-dimensional before it can be used for modeling. The floor area data is reshaped into a two-dimensional format so it can be used by Scikit-Learn. Each floor area value becomes one row in a single column feature matrix, matching the structure Scikit-Learn expects when fitting a model. To predict the price for a new apartment, we create a two-dimensional NumPy array containing the floor area, 725 square feet. The extra brackets are important because Scikit-Learn expects prediction inputs to be two-dimensional, even for a single sample. Before training the model, the input features must be checked to make sure they are two-dimensional, as required by Scikit-Learn. In this case, the reshaped floor area data is validated before fitting. If it is not in the correct shape, an error is raised so the problem can be fixed before model training begins. The code verifies that the feature data and target values are aligned by checking that they contain the same number of samples. If they do not match, it raises an error to prevent training with inconsistent input data. We create a linear regression model in Scikit-Learn to predict rent from floor area. Training the model means fitting it with the floor area data as the input and rent prices as the target, so it can learn the relationship between them and make predictions for new floor areas. The trained linear regression model predicts the rent for a new apartment from its prepared feature data. The prediction returns a list-like result, so the first value is taken as the estimated rent. This converts the model's learned relationship between floor area and rent into a specific prediction for the apartment size. The output checks that the data is in the right form for Scikit-Learn and then shows the model's prediction. It confirms the library version, verifies that the floor area data has been reshaped from a flat array into a two-dimensional feature matrix, and checks that the rent targets match the number of samples. It also confirms that the new apartment is represented as a single two-dimensional sample before displaying its predicted rent as a whole dollar amount. This script shows why Scikit-Learn data must be shaped correctly before training a model. Floor area values are converted into a two-dimensional feature matrix, while rent prices remain the target values, and the new apartment's area is prepared the same way for prediction. After checking that the shapes are compatible, a linear regression model is fitted and used to estimate the rent for a 725 square foot apartment. DataFrame inputs. Pandas DataFrames work well with Scikit-Learn because they keep data in a clear table, with rows as observations and columns as features. Scikit-Learn estimators expect a two-dimensional table, even when using only one feature, so avoid passing a single column as a one-dimensional series. Keeping the data as a data frame preserves column names and makes the structure easier to inspect before fitting. Data frames are useful for datasets with mixed feature types, such as numbers, categories, dates, and text indicators. They make it easier to select and transform columns by name, which helps prepare data for Scikit-Learn models that usually require numeric inputs. Even with meaningful column names, the data must still stay rectangular, with rows kept consistently aligned. When preparing data frames for modeling, keep predictor columns separate from the target values. Including the target in a feature table can make performance look falsely high, because the model may learn from the answer itself. After any data changes, make sure the feature rows and target values stay in the same order, and confirm that the model input is a properly aligned two-dimensional table. Python code. Data frame inputs. Data frames help keep feature tables two-dimensional, which is important for Scikit-Learn inputs. Selecting columns in different ways can change the input shape, so the output highlights the difference between correct and incorrect formats. We import pandas for working with tabular data. Bring in Scikit-Learn's logistic regression model for machine learning, and load Scikit-Learn itself for version information and utilities. Together, these imports prepare the environment for data handling and model training. We create a small in-memory pandas table to organize patient data for analysis. It includes each patient's age, cholesterol level, and diagnosis status, where 0 means not diagnosed and 1 means diagnosed. This structure makes the data easy to work with in pandas and machine learning tools. We prepare the data for model training by choosing age in years and cholesterol level as the input features. These columns are separated into a feature dataset, while the diagnosis column is kept as the target. This clearly separates what the model will learn from and what it will try to predict. Selecting the age years column as a data frame keeps the data two-dimensional, which many Scikit-Learn functions require. Selecting the same column as a series makes it one-dimensional. This shows how the way you select a column affects its structure and compatibility with later processing. Before training, the code checks that the feature data is two-dimensional, as required by Scikit-Learn, and that it has the same number of rows as the target values. This ensures each set of features matches one target value. If the data is not structured correctly, the code raises an error instead of fitting the model. We create a logistic regression model with a fixed random state, so results can be reproduced. The model is then trained on age and cholesterol data to learn how these features relate to whether a patient is diagnosed. Once trained, it can use that learned relationship to predict outcomes for new patients. We first check the Scikit-Learn version to support compatibility and reproducibility. Then we inspect the shapes of the feature data, a single-column data frame, a single-column series, and the target variable to confirm their dimensions and alignment for training. Finally, we review the feature names to verify which columns the model uses. This script shows how to use a data frame as input to a Scikit-Learn logistic regression model. It separates patient features, such as age and cholesterol, from the diagnosis target, and emphasizes that feature data should stay two-dimensional, even when using only one column. It checks that the features and target are aligned, trains the model, and prints key shapes and feature names to confirm the input data is set up correctly. Sparse matrix inputs. Sparse matrices are useful when data has many features but most values are zero, such as after text vectorization or one-hot encoding in Scikit-Learn. They store only the non-zero values and their positions, which saves memory and can make computation faster. Even in sparse form, the data must remain two-dimensional, with each sample as a row and each feature as a column. When using sparse inputs in Scikit-Learn, choose a format the estimator supports well, such as compressed sparse row for sample-based processing or compressed sparse column for feature-based access. Many models, including linear models and naive Bayes, can work directly with sparse data, but others may convert it to dense form and use too much memory. For large datasets, keeping the data sparse is essential to avoid memory problems. With sparse inputs, keep feature columns in the same order during training, validation, and prediction, so each column always represents the same feature. This is especially important for text vectorizers and categorical encoders, where a shifted column can lead to incorrect predictions. Sparse matrices should contain numeric values, so raw strings or mixed types must be converted first. Used properly, they provide an efficient sample-by-feature table without storing large numbers of zeros. Python code. Sparse matrix inputs. Sparse matrices store mostly zero features efficiently, but Scikit-Learn still requires data to be arranged as a two-dimensional feature table. This example focuses on checking the table's shape, data type, and memory use. We import key Python libraries for a text classification workflow. NumPy supports efficient numerical operations, while pandas helps manage structured data. Scikit-Learn provides tools to turn text into token count features and to train a logistic regression model for binary classification, along with access to broader machine learning utilities. A small set of simple sentences is used to build a document term matrix. This matrix counts how often each word appears in each sentence, creating a sparse numerical representation of the text. This step converts language into a format that machine learning models can process. We create a NumPy array of labels to store the target class for each document. Each label is either 0 or 1, and the order matches the document order, so the model can learn from the correct document label pairs. A CountVectorizer converts text documents into numerical data by learning the vocabulary and counting how often each word appears. After fitting and transforming the documents, it produces a sparse matrix that stores only non-zero word counts, making it memory efficient. This matrix provides the word frequency features needed for machine learning models. The code confirms that the sparse matrix is in the expected samples by features format. It checks that the input is two-dimensional, as required by Scikit-Learn. If not, it raises an error, so incorrectly shaped data is caught before further processing or modeling. The code verifies that the feature matrix has the same number of samples as there are target labels. If the counts differ, it raises an error to signal that the features and labels do not align, which must be fixed before training a model. The code compares the memory use of a sparse matrix with the same matrix stored densely. It measures the dense version's total bytes, then adds the bytes used by the sparse matrix's non-zero values, their positions, and its pointer information. This shows how sparse storage saves memory by recording only non-zero entries and where they belong. We first get the vectorizer's feature names, so each column in the document term matrix can be linked to its word. Then we convert the sparse matrix into a dense pandas data frame and use those feature names as column headers. Finally, we preview a small section of the data to quickly check its structure and contents. We create a logistic regression model with a fixed random state for reproducibility and enough iterations to help it converge. Because it can work directly with sparse input, it is efficient for the feature matrix. We then train it on the sparse features and labels, so it can learn the relationship needed to make predictions. To classify new short text documents, we first convert them into numerical features using the vectorizer that learned the training vocabulary. This produces feature vectors in the same format the model expects. The trained logistic regression model then predicts the most likely class for each new document based on the patterns it learned during training. This section checks key details of a Scikit-Learn workflow using sparse data. It reports the library version, the shapes of the feature matrix, and target labels, the matrix data type, and the number of non-zero values to confirm the data is structured correctly. It also compares dense and sparse memory use to show the efficiency of sparse matrices, previews part of the dense data, and displays logistic regression predictions for new samples. This script shows how Scikit-Learn works with sparse document term matrices created from text using a CountVectorizer. It verifies the matrix shape, compares dense and sparse memory use to show the storage savings, and previews the data with feature names. It then trains a logistic regression model directly on the sparse matrix and uses it to predict labels for new text documents, while reporting key details such as matrix size, data type, non-zero entries, memory usage, and predictions. Shapes and dtypes. Feature matrix shape. In Scikit-Learn, the feature matrix must be two-dimensional, with each row representing a sample and each column representing a feature. This structure tells the estimator which values are observations and which are variables. Even when there is only one feature, the data should still be shaped as a two-dimensional matrix, so the model interprets it correctly. Shape problems can happen when data is accidentally flattened, transposed, or reduced during preprocessing. This may cause samples and features to be mixed up, leading to errors or poor model fitting. Because NumPy arrays, pandas DataFrames, and sparse matrices can handle dimensions differently, always check that rows match the target values and columns represent the predictors before fitting a model. A model expects prediction data to have the same feature matrix shape and meaning as the data used during training. If columns are missing, added, or reordered, the model's assumptions can break and lead to errors or unreliable results. Checking the feature matrix shape after transformations helps keep training, validation, and prediction data aligned and easier to debug. Python code. Feature matrix shape. This example highlights the importance of feature matrix shape in Scikit-Learn. Feature inputs must be two-dimensional, and the output contrasts an incorrect shape with the correct one. We import key Python libraries for a machine learning workflow: NumPy for numerical operations and arrays, pandas for working with tabular data, and Scikit-Learn's linear regression model for building a regression model. We also import Scikit-Learn itself to check version information for compatibility and debugging. We create two one-dimensional NumPy arrays, one for Celsius temperatures and one for matching energy consumption in kilowatt hours. These paired values provide the data needed to examine how temperature relates to energy use. The assigned temperature data is only one-dimensional, so it is not a valid feature matrix for Scikit-Learn. Scikit-Learn expects feature inputs to be two-dimensional, with samples as rows and features as columns. Passing a one-dimensional array would cause an error when fitting a model. The temperature data is reshaped so it matches the format expected by Scikit-Learn. The reshape method turns the one-dimensional data into a two-dimensional feature matrix, where each temperature is one sample with one feature. Using -1 and 1 lets NumPy choose the number of rows automatically, while keeping a single feature column, making the data ready for model fitting. Create a pandas data frame from the temperature data to organize it in a table with a temperature column. Then, select that column in a way that keeps the result as a two-dimensional data frame, which is the format Scikit-Learn expects for feature data. Before training, confirm that the feature matrix has the same number of rows as the energy target values, so each temperature matches one energy measurement. Then create a linear regression model and fit it with the aligned temperature and energy data. This trains the model to learn the relationship between temperature and energy consumption. The example checks that the data is in the right shape for Scikit-Learn before making a prediction. It confirms the library version, shows that a one-dimensional feature array is invalid, and compares it with correct two-dimensional feature matrices, including one made with pandas double brackets. It also verifies that the feature rows match the target values, then uses the trained model to predict energy consumption at 22 degrees Celsius in kilowatt-hours. This script shows that Scikit-Learn feature data must be two-dimensional, with each sample as a row and each feature as a column. A one-dimensional temperature array is reshaped or placed in a pandas data frame, so it can be used correctly with linear regression. The script also checks that the feature rows match the target values before fitting the model, then predicts energy use for a temperature of 22 degrees Celsius. Target shape checks. When preparing data for a model, make sure the target values match the number of observations in the feature matrix. Each input record should have one corresponding label, so the model can correctly connect features to outcomes. This check is especially important after filtering or merging data, where mismatches can easily cause fitting errors. For single output prediction tasks, the target data should usually be one-dimensional, such as a list of labels or values. Errors can occur if it is accidentally kept as a two-dimensional structure, which often happens when selecting a column from a pandas data frame as a data frame instead of a series. Before fitting the model, check the target shape to make sure it matches what the model expects. Some tasks need a two-dimensional target, such as predicting multiple outputs or assigning several labels to one sample. In these cases, each sample has one target row with multiple columns. Before fitting the model, confirm that the target shape is intentional, that every feature row matches a target row, that the columns reflect the prediction task, and that the estimator supports this format. This helps prevent errors and keeps the training data consistent. Python code target shape checks. This script checks whether target arrays have the right shape before fitting a model. It compares valid and invalid targets and reports clear, beginner-friendly decisions about which shapes are acceptable. These imports prepare the tools needed for a basic machine learning workflow in Python. NumPy supports numerical work with arrays and matrices, while Scikit-Learn provides the iris dataset and the logistic regression model. Together, they allow you to load data, prepare it, and apply a classification algorithm. We load the iris dataset from Scikit-Learn, a common dataset for classification. The flower measurements are stored as the feature data, and the species labels are stored as the target data. This prepares the dataset for analysis or model training. The target data is prepared in several forms to illustrate common classification cases. A normal one-dimensional label array represents a standard single output task, while a one-column two-dimensional version is used when a method requires that shape. A shortened version shows the error caused when labels and samples have different row counts. A two-column version represents multi-output classification, with each column indicating a separate binary target. A collection of target arrays is used to compare how different target shapes work with a feature matrix during model fitting. A one-dimensional target is appropriate for single output classification, while a two-dimensional single-column target is often flattened back to one dimension. A shortened target shows what happens when the number of rows does not match the features. And a two-column target represents a multi-output classification setup. The script first shows the Scikit-Learn version to confirm the software context and compatibility. It then displays the shape of the feature matrix, helping verify that the input data has the expected dimensions before further processing. The code reviews each target array and checks whether its row count matches the number of samples in the feature data. It also formats each target's shape for readability, then prints the target name, shape, and alignment status. This gives a quick check that each target is properly matched to the input features. Flatten the target data into a one-dimensional form so it can be used correctly for model fitting. Then create a logistic regression model with a fixed random state and a higher iteration limit, and train it on the feature data and target values for classification. We verify that the corrected target array matches what the logistic regression model expects by checking that the flattened target is one-dimensional. This confirms it is suitable for a single output classification task. We then confirm the model was fitted successfully by checking that it has learned its class labels, shown by the presence of the class's attribute. This script shows why target shape matters when training logistic regression in Scikit-Learn. Using the iris dataset, it compares several target formats, including a normal one-dimensional target, a column-shaped target, a shortened target, and a multi-output style target. It checks whether each target has the same number of rows as the feature data, then flattens the column-shaped target so the model can use it correctly. The main lesson is that classification models expect targets with compatible dimensions, and reshaping or mismatch lengths can cause fitting problems. D-type checks. When preparing data for Scikit-Learn, check both the shape of the data and the type of values in each column. A model may fail if numbers are stored as text, if a column mixes measurements with labels such as not measured, or if categorical and text data have not been converted. Before fitting a model, make sure each feature is in a format that the estimator and preprocessing steps can handle, since many Scikit-Learn tools expect numeric arrays. Checking data types ensures that numbers are used in the right way before fitting a model. Some numbers, like postal codes or product IDs, are labels rather than true numeric values, while values like temperature or account balance are genuinely numeric. Classification labels may be strings or numbers if they represent categories, but regression targets should be numeric because they predict continuous values. Correct data types help the model interpret the data accurately. Check data types throughout loading, cleaning, preprocessing, and fitting, because preparation steps can change them in unexpected ways. Missing values may turn integer columns into floating point values or appear as text, which can prevent numeric conversion. Sparse data and floating point precision also affect memory use, estimator compatibility, and numerical stability. Regular D-type checks help ensure the data keeps its meaning and is ready for the estimator. Python code, D-type checks. This example verifies that the data types are ready before fitting a model. It separates numeric measurements from labels and checks that the target has the expected shape and type. We import NumPy for efficient numerical work, pandas for handling structured data, and Scikit-Learn's linear regression tool to build a model that predicts outcomes from input features. We create a small pandas dataset about houses to demonstrate common data type problems. It includes house area, prices stored as text with currency symbols and commas, and postal codes stored as numbers. The key issue is that text-formatted prices must be cleaned before they can be used in analysis. Before cleaning or transforming the data, we first inspect how pandas is storing each column's data type. We display the DataFrames data type information in a readable form, which helps confirm the current structure of the data and identify any columns that may need conversion. Clean the price text by removing $signs and commas, then convert the result into numeric values with pandas. Store the converted prices in a new price in US dollars column, so the data is ready for analysis. To prepare the housing data for linear regression, the area column is converted into a numeric feature array, and the price column is converted into a numeric target array. Using floating point values ensures both inputs are in the format the model expects for training. Before fitting the model, confirm that the data is ready for the estimator. Check that the feature matrix and target vector have compatible shapes, and verify that both use suitable floating point data types for numerical regression. These quick checks help prevent formatting issues before model training begins. We create a Scikit-Learn linear regression model and train it using the input features and target prices. During training, the model learns how area in square meters relates to price in dollars by adjusting its parameters to reduce prediction errors. We first check how pandas stores the postal code column. Then, note that postal codes are labels rather than continuous measurements, so they should not be used as regression features. We also confirm that the target values form a one-dimensional vector, which is required for fitting the model. Finally, we report the linear regression slope, rounded to 2 decimals, as the change in price per square meter. This script shows how to prepare data for linear regression by checking and cleaning data types before fitting a model. It converts price values stored as text into numeric values, then uses area as the feature and cleaned price as the target. It also confirms that the arrays have the right shapes and numeric types, while noting that postal codes should not be treated as ordinary numeric features. After fitting the model, it reports the slope, which represents how price changes per square meter. Inspection utilities. Bunch data containers. In Scikit-Learn, a bunch is a dataset container that works like a dictionary, but also lets you access items by name. Built-in datasets often use it to keep the data matrix, target values, feature names, target names, and description together. This helps show that a dataset includes not only numbers, but also their meaning and metadata, making it easier to understand before fitting a model. The bunch container in Scikit-Learn keeps a dataset's features and target values organized together, making it easier to check whether the data is ready for an estimator. It does not clean the data, but it supports inspection, comparison, debugging, and understanding how estimators behave. This predictable structure helps make data analysis and model evaluation more reliable. Bunch containers in Scikit-Learn make datasets easier to interpret by pairing the data with useful metadata, such as feature names and target labels. This helps connect model results to real variables instead of anonymous columns. By keeping data and meaning together, they support clearer analysis and more understandable model evaluation. Python code. Bunch data containers. Before modeling with Scikit-Learn data, inspect the bunch container to understand what it holds. Match each array to its names and metadata. Then run a few compact checks to confirm the data is ready to use. We import the load iris function from Scikit-Learn to access the classic iris dataset. It returns the data as a bunch object, which works like a dictionary while also allowing attribute-style access. This makes the dataset easy to explore and use in later steps. We load the iris dataset using Scikit-Learn's load iris function. It returns the data as a bunch, which works like a dictionary, but also lets you access items as attributes. This makes it easy to use the dataset along with metadata, such as feature names and target names. The code checks that the iris dataset object is a Scikit-Learn bunch container, then displays its first few keys. This gives a quick view of the main data and metadata fields stored in the dataset. We extract the iris dataset's feature matrix and target labels, then check their shapes. The feature matrix shows how many samples and measurements are included, while the target vector confirms there is one label for each sample. This verifies that the data is properly structured before modeling. The code displays the first 3 feature names in the iris dataset to clarify what the feature columns represent. It also shows the target class names, helping connect each label to its meaning and making the dataset easier to interpret. First, we verify that the feature data and target labels contain the same number of samples. This confirms that every input has a matching label, so the dataset is properly aligned for supervised learning. This checks whether a bunch container returns the same data object through attribute access and dictionary-style key access. Using an identity comparison confirms that both access methods point to the exact same object in memory, so they retrieve the same underlying data. This script shows how Scikit-Learn stores the iris dataset in a bunch object, which can be used like both a dictionary and an object with attributes. It checks the dataset's keys, extracts the features and targets, and confirms their shapes are suitable for modeling. It also reviews the feature and target names, then verifies that key-based and attribute-based access return the same data. Overall, the script is a quick data inspection step before training a model. Cloning estimators. Cloning an estimator in Scikit-Learn creates a new estimator with the same settings but none of the learned data. This separates the model's configuration from results gained during fitting, such as coefficients or cluster centers. The cloned estimator can then be fitted independently, which helps keep inspection and evaluation reliable. Cloning helps Scikit-Learn evaluate models fairly by starting each training run with a fresh estimator that keeps the same settings, but has no learned information from earlier runs. This prevents results from being biased during cross-validation, pipelines, and grid searches. It ensures each data split or model configuration is tested independently, without leftover parameters or transformations. Cloning in Scikit-Learn separates a model's configuration from what it has learned from data. It copies the estimator's settings but removes learned attributes, so experiments can be repeated without carrying over past patterns. This helps keep analyses independent, such as when applying the same model setup to different business regions or student cohorts, and supports more reliable evaluation and inspection. Python code, cloning estimators. This example explains estimator cloning. A clone keeps the estimator's settings, but does not keep anything it learned during fitting. The comparison shows the difference between a fitted estimator and its cloned version. This setup imports key Scikit-Learn tools for a simple classification workflow. It includes the clone function to copy an estimator without learned data, the iris dataset loader for a standard classification dataset, and the logistic regression class to build a linear classifier. We load the classic iris classification dataset from Scikit-Learn, then separate it into feature data and target labels. This split keeps the inputs distinct from the values the model is meant to predict, which is essential for training and evaluation. Before training, the code verifies that the input data has the expected shape. The features must be two-dimensional, and the target must be one-dimensional. If the data does not match this structure, it raises an error. This check helps prevent training failures by catching formatting problems early. The code verifies that the feature data and target values have matching lengths before model fitting. If they do not match, it raises an error, helping ensure every feature row has a corresponding target value. We create a logistic regression model with a set iteration limit and fixed random state to make training reliable and reproducible. Then, we train it on the iris dataset features and target labels, so it can learn how the inputs relate to the flower classes. The Scikit-Learn clone function creates a fresh copy of the original logistic regression model. It keeps the same hyperparameter settings, such as maximum iterations and random state, but does not copy anything learned during fitting. As a result, the cloned model is ready to train on new data with no prior learned state. We compare the original model with its clone to confirm they share the same hyperparameter settings, meaning the configuration was copied correctly. Then we check whether each model has learned from data by looking for the learned classes attribute. The original should have it after fitting, while the clone should not, showing that cloning copies the setup but not the trained state. This example checks that cloning a Scikit-Learn model copies its settings but not its learned state. After confirming the library version, it compares the original and cloned model hyperparameters, then verifies that only the fitted original has learned class information. It also confirms that the clone is a separate object in memory, showing that cloning creates an independent, unfitted model with the same configuration. This example shows that cloning a Scikit-Learn estimator copies its settings, but not what it has learned from data. A logistic regression model is trained on the iris dataset, then cloned. The original keeps its fitted information, such as the learned classes, while the clone has the same hyperparameters but is still untrained. The two models are separate objects, making cloning useful for resetting a model while preserving its configuration. Feature name inspection. Feature name inspection checks whether a Scikit-Learn estimator keeps track of the input column names it was trained on. This is especially useful with pandas DataFrames, where columns have meaningful names rather than just positions. By storing and checking these names, an estimator can help detect swapped or missing columns and keep predictions aligned with the intended variables. Feature name inspection helps ensure that new data matches the structure used to train a model. Instead of relying only on column position, it checks that inputs like employment length or debt-to-income ratio are correctly identified, reducing the risk of misinterpreted features. This also makes complex data pipelines more transparent and auditable, especially when raw fields are transformed into model-ready variables. Feature name inspection makes models easier to discuss and debug by showing meaningful field names instead of relying on column positions. It helps teams confirm that the model is using the expected data and that unexpected fields have not entered the workflow. Although it does not replace validation or testing, it makes the data structure clearer and helps ensure the model uses the right information. Python code. Feature name inspection. After fitting an estimator, check the feature names it stored and compare them with the input data, especially when switching between pandas data and plain arrays. Before making predictions, Confirm that the columns are in the expected order to avoid mismatched features. We import pandas to organize and manage the data, and use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in logistic regression, which is used to build a classification model for the dataset. We create a small pandas data frame with labeled columns for age, income in thousands, and debt ratio. Each column contains sample values for different individuals, giving us structured data that can be used to train machine learning models. The target for the model is a one-dimensional list of binary class labels, with one value for each row in the training data. Each label indicates whether that observation belongs to class 0 or class 1. In supervised learning, the logistic regression model uses the input features to learn how to predict these labels. We create a logistic regression model with a fixed random state, so the results can be reproduced. Then we train it on the training data and target values, allowing the model to learn how the input features relate to the outcomes and make predictions. We check the feature names saved by Scikit-Learn when the model was fitted, along with the Scikit-Learn version being used. This confirms which training columns the model expects and helps ensure future input data matches the same structure. A new scoring dataset is created with the same columns as the training data, but in a different order to mimic a possible prediction time mismatch. Only the first two rows are used for simplicity. The column names are then collected into a list and printed, so the current order can be checked against the expected order later. Before making predictions, the scoring data's columns are checked against the order used during model training. The columns are then reordered if needed, so the model receives features in the expected format. This helps prevent errors and supports accurate predictions, after which the results, and whether the original order was correct, are displayed. This example shows why feature order matters when using pandas data frames with Scikit-Learn models. A logistic regression model is trained on columns such as age, income, and debt ratio, and Scikit-Learn records the feature names from training. When new data has the same columns in a different order, the columns are reordered to match the training order before prediction. This helps ensure the model receives each feature in the expected position and produces reliable predictions. In this lecture, you learn to prepare NumPy, pandas, and sparse inputs that satisfy Scikit-Learn shape requirements. Identify dtype and target shape issues before fitting estimators. And use dataset containers, feature names, cloning, tags, and diagrams for inspection. In the next module, Module 3, we will go over datasets.
Thank you for your attention. See you all in the next lecture.